Okay, all you limit lovers, we are back, and today we're talking about limits at infinity. Now, we've looked at these from a graphic standpoint before, so hopefully you have that visualization that when you talk about what's the value of the function as x goes to infinity, you're talking about the right side of the graph. And as x goes to negative infinity, you're talking about the left side of the graph. You know, you're talking about the end behavior of the function. What's happening to it in the long run? Is it leveling off at a horizontal asymptote? Is it taking off to infinity, you know, unbounded growth, or negative infinity? So if you really know your end behavior kinds of rules, or you can reason those things out, that's really the key to these limits. They're actually probably the easiest ones. So I've summarized these rules here that you should know if you're talking about pure polynomials and that kind of behavior: even positive, even negative, odd positive, odd negative. The horizontal asymptote rules for rational functions. And again, what makes a rational function is if it has a polynomial over another polynomial, the quotient of two polynomials. You compare their degrees. If they have equal degree, that means it will be a horizontal asymptote at the ratio of the leading coefficients. If the denominator degree is greater than the numerator degree, that means your denominator is growing faster, so your fractional value is getting smaller and smaller, and you'll always be leveling off at 0. And if the numerator degree is greater than the denominator, that means that the top of the fraction is growing faster than the denominator, so the overall value is getting larger. It's not going to be leveling off. It has no horizontal asymptote. And then if you really want to go further to know if it goes to infinity or negative infinity, that's when you have to reduce and follow your rules for end behavior. So let's just see a bunch of these here. The beautiful thing about these is a lot of them don't take a lot of work, just reasoning out and recognition. So when these are mixed in with all your other limits, just keep in mind the two different types you're really dealing with. If x approaches a number, that's when you're talking about all the things we've been doing lately. Try to substitute it in, try to factor, whatever. But if you're talking about x going to infinity or negative infinity, what's happening in the long run? HA, no HA? So in this case, x going to infinity, you've got a rational function here. You should be zeroing right in on that degree of numerator compared to denominator. The degree of the numerator is 1. The degree of the denominator is 2. If your denominator degree is bigger than your numerator degree, it's automatically a horizontal asymptote of 0. That means the y values of the function are automatically approaching 0. That's your limit answer. Beautiful. And with rational functions, when they have a horizontal asymptote, they approach that value on both sides. It levels off. So when we talk about x going to negative infinity, that's the left side of the graph. Well, this is the same function. It's still going to be approaching 0. And feel free to graph these if you want to see that visualization. Remember, we used to talk sketching these by hand, how the graph goes towards the asymptote like a magnet on the ends. Number 3, x going to negative infinity. I've got another rational function here, two polynomials. Take a look at those terms. Those degrees are equal. And now that means we have an HA at the ratio of those leading coefficients because they're growing at the same rate, so it's kind of like they cancel each other out. But negative 8/12, which reduces to negative 2/3. That would be the horizontal asymptote, and that's the value, whether I'm going to the left or the right. X going to infinity, got another rational function here. The numerator is greater than the denominator degree, so that means we have no horizontal asymptote. That means you're talking about one of these scenarios. It's either going to infinity or negative infinity. So one way to answer this is if you take that approach of, hey, infinity, negative infinity, those are not numbers. That's unbounded growth. I could just stop right now and say DNE unbounded. However, there is a chance that your teacher or the AP exam next year might want to know, well, which one is it doing as we go to the right? Is it going towards, infinity? Is it going up? Or is it going to negative infinity? So just remember to determine that you do the ratio of these and x to the fourth divided by x squared is positive x squared. Take into consideration any coefficients, positive, negative. And we have x squared. Now x squared is an even positive polynomial, and that's how this rational function would behave on both sides. So as we go to positive infinity, that would be the right side of the graph. Our graph is going to be going up. So you also could answer just pure infinity for this, and that would be acceptable, I think, by most teachers, or your teacher might prefer it. So I just like to keeping you flexible here on the two ideas. Same function. This time we're talking about the left side. So I mean, it's still the same thing we were looking at here of an even positive kind of end behavior with a bunch of stuff in the middle maybe, but the left side is still going up. So again, you could just say DNE unbounded. I would definitely accept that. But you also could say it's going up to infinity. Number 6 here, the limit of this as x approaches negative infinity. You've got you got 12x to the fifth over negative 6x squared. Those two terms, again, your numerator is bigger than your denominator, so you definitely could stop and say, hey, DNE unbounded. If you want to go a little further and know exactly which type of unbounded behavior, that's where you do the ratio of these coefficients, which would reduce to negative 2x to the third, 12 divided by negative 6. Watch that sign. Subtract your exponents. That means in the long run, this thing is going to behave like an odd negative polynomial. So an odd negative polynomial is up on the left, down on the right, and this graph might have some VAs and things like that in the middle, but I know it's behaving like this. X going to negative infinity is asking for the left side of the graph, which is going up. So you could say infinity. Hopefully all these end behavior kinds of rules are coming back to you, because the limit notation is pretty similar to what we used when we described end behavior. So I'm just hitting out a bunch of examples so you see just about every little version of this, and some hopefully some ones that make you think a little bit more on the backside. But these are the kind of straightforward ones. This x approaching infinity, hey, you got this. It's in factored form, which is great for zeros and all that, but kind of annoying for this. So just keep in mind you've got x to the third, x squared. That's an x to the fifth degree. In the bottom you've got x to the first and x to the fourth. That's also x to the fifth, which means we need the ratio of those leading coefficients for our HA. So take some time and think about what those leading coefficients would be. That would be negative 2x to the third, and when you cube that, you would get negative 8x to the third times the leading term from this binomial would be 9x squared, and that would give you negative 72x to the fifth. And of course there'd be a bunch of other terms. I don't want you to think it works like that, but we're only after that lead term. And down here it would be 7x times x to the fourth, nothing crazy there, so 7x to the fifth plus blah blah blah. And that means you're going to have an HA, horizontal asymptote, at negative 72/7. And so that's the answer to your limit. This is not technically a rational function because this is not a polynomial. However, you can think of it along the same lines. I mean, all these rules really come from just the major idea of, if you got a fraction, what's growing faster, numerator or denominator? Or are they the same rate? That's really the idea. If the denominator is growing faster, its value is going to approach 0. If the numerator is growing faster, then it's going to infinity or negative infinity. It's increasing without bound. So let's just think about this. You can think about essentially this degree is like root 5 x to the 1/2. The square root of x is x to the 1/2. And in the denominator, this is really 2x to the first. The denominator has a larger degree. You're going faster. This thing would have a horizontal asymptote of y equals 0. So the answer is 0. Check it out on the graph if you like. Okay. Now let's take it up a notch on the back side here. Some still pretty easy, but number 9 here, this you've got two fractions, x approaching infinity of 4/3 minus 5 over 2 x squared. One thing you might like to do is make a single fraction out of that by making a common denominator and putting those two things together. So let's just think about that here. The common denominator would be 6x squared. So you'd have to multiply this one by 2x squared. And so that means the numerator would give you 8x squared minus, and this 6x squared means you have to multiply that by 3, 15. And so you're really looking at the limit as x approaches infinity of 8x squared minus 15 all over 6x squared. And maybe now it's a little more clear-cut that, hey, equal degree, ratio of the coefficients is my HA. That's the answer to my limit, 4/3. Done. But it does bring up a property, just so you know, that you could have approached it this way, that one of the things about limits is it's an operation that can essentially be distributed to terms, meaning I could evaluate these limits individually. The limit of 4/3 as x goes to infinity is just 4/3. It's not gonna change. There's no variable. Minus the value of the limit of this fraction. That's got a greater degree in the denominator, so its limit as x approaches infinity is 0. So you get 4/3 that way too. So it doesn't matter to me, but it's kind of nice to know that you can do that with limits. You know, a lot of operations in math, you can't sort of distribute it to terms, but this you can. And if you try that here, though, you might run into a problem that, you know, approaching negative infinity for these fractions, this one certainly has a limit of 0, but this one has an x on the top, no variable in the denominator, so that would be sort of a DNE, unbounded, and you know, DNE minus 0, that's maybe hard to think about. At least you don't want to take chances. So I would take the step and just convert this to a single fraction, which would be 4x cubed. So I need to multiply that by x cubed. You got x to the 4th minus 4 there. And now you can really see that numerator is greater than the denominator. So that's a DNE unbounded. It's not leveling off. Or if your teacher wants to know exactly what it's doing, this is x to the 4th divided by 4x cubed, which is 1/4 x to the 1st, which is, I mean, it's linear actually, but it's an odd positive, which means up on the right, down on the left, you know, positive slope. And x going to negative infinity is the left side, so this thing is going down on the left. So you could also say negative infinity if you like. All right, here we go. What would it be without some trig mixed in there? What is the limit of sine of x as x goes to infinity? Now I picked a nice one here. Sine of x, you really should know that graph. That goes like this, right? And it just cycles back and forth. The highest it ever goes is 1. The lowest it ever goes is -1. And as you go to infinity, it doesn't level off, but nor does it grow without bound. It just oscillates between these values and cycles back and forth and never gets particularly close to anything. So this is sort of the rare case. We haven't seen it that often, but this is an example of DNE oscillating. Now this, almost the same limit, except I threw an over x in the denominator. Now how does that change things, or does it at all? That you can't think of this like a rational function because this is a trig expression. It doesn't have degree like a polynomial. But we can think of it as in how do these things compare? As you go to the right, as x gets larger and larger, think about that denominator. That denominator will be things like 10, 100, 1,000, etc. Your numerator is sine of x. No matter what you plug in for x, it's never going to get any bigger than 1, and it's never going to get any smaller than -1. So, you know, maybe you get at most 1, or at smallest -1, or at biggest 1, or, you know, some decimal in between. But what's the overall value of this approaching? It's approaching 0. And it's that same principle that we talked about on the front, that if the bottom is growing at a faster rate than the numerator, that's going to make the overall value approach 0. So sometimes that throws people off a little bit. They think, hey, it's DNE oscillating because of the sign, does oscillate, but it's the overall value that we're talking about. And that value will go positive to negative, but each time it'll get closer and closer to being zero as you go further and further along. So sometimes you just got to stop and think about these things a little bit. It's not always just a rule or a formula you plug into. And now we've got an exponential function. Again, not a polynomial, not a rational function, not a trig function, an exponential, e to the x plus 5. Again, I intentionally picked one that should be pretty easy, that you can either think of the graph or just think about when you plug in bigger and bigger x values, what's going to happen to the value of this function. But if you want, just for a little review of graphing, this is an exponential growth because the base is bigger than 1, and it's moved up 5 units. So it looks like this. If you remember, every exponential function had a horizontal asymptote at 0 normally, but now it's looking like that. And on this graph, as we go to the right, this graph is going up. It's growing without bound. That's DNE, unbounded. Or if you want to say specifically what value, is it approaching, you could say infinity. It's going up. But on this same graph, as we talk about the left side, as x goes to negative infinity, I'm not going to redraw the graph, it's the same thing. On the left side, though, it's approaching that horizontal asymptote. So the value will actually be approaching 5. So keep in mind that although exponential functions have horizontal asymptotes, unlike rational functions, they don't necessarily approach that same value on both sides of the function. In fact, they often won't. But rational functions always do approach that HA from both sides, left and right. So if you got exponential, you might have to just think a little bit more about which side are we talking about. Are we going towards that HA, or are we veering away from it? And lastly here, if you're still sticking with me, that's good. Feel free to leave a comment or a thumbs up, or, no bonus points today, but keep listening. Who knows, maybe in the future. And this one here, we have sort of a ratio of exponential functions. This was a good AP question from a few years ago, asking about this, and this throws people off. But just think about it is what I would suggest. If you plug in infinity to this, or as you are approaching infinity, plugging in 100, plugging in 1,000, you'd be plugging it here and there. Right now, 2 to the 100th is a huge number, -5. That doesn't really take away much from it. It's basically going to be pretty close to whatever 2 to the 100th is. But in the denominator, you're going to have the same 2 to the 100th value, but plus 7. Again, not changing it that much. If you go to the thousandths, or the 10,000ths, you just keep adding. This 5 and 7, they're going to have less and less of an impact on this overall value. They're basically going to be negligible, and you're going to be talking about the ratio of this compared to this, and it's going to get closer and closer to being 1. So it's almost like the idea of they're growing at the same rate, and it's the ratio of those things. So ratio of those coefficients, if you like, it's 1. On this side, hey, maybe it's the same thing, maybe just 1. Maybe I don't even have to think about it. Except you're talking exponential. So remember, as you go to negative infinity, now you're talking about, 2 to the negative 100th, for example, over 2 to the negative 100th, and then plus 7. Now in this case, 2 to the negative 100th, remember, a negative exponent doesn't make a negative number, it makes a reciprocal. So it would make 1 over 2 to the 100th. And 1 over 2 to the 100th is very close to being 0. And as you go further and further to the left, you make that negative 1,000, negative 10,000, negative 1,000,000, etc. This is only going to get closer and closer to being 0. But then you're going to be subtracting 5 from it. And same thing goes down here. This is going to, that portion of it is going to approach 0, but then you're going to add 7 to it. So you're actually going to get negative 5/7. So this actually, if you were to graph this function, it actually has 2 horizontal asymptotes. And that doesn't happen that often, in the things we've explored at this level, but, you can check it out here. First of all, if you want to see what is negative 5/7 worth approximately, it's about negative 0.714. And now if I put this graph in, and I've already typed it in, I adjusted my windows to give me x values of negative 20 to 20, and that's not even close to being infinity, but it should give us a wide enough view. There's your y values. I only went from negative 3 to 3 because that's all I'll really need. And you see that graph, you see how it's leveling off on the right side and on the left side, but at two different y values. On the left side, as I keep going to the left, look at that y decimal. It's just getting closer and closer to being that negative 0.714, blah, blah, blah. That's the negative 5/7. And out here, on the right side, of course, you're getting this fraction. I'm not sure. And as you go further and further, it's getting closer and closer to being 1, 0.99999, 0.99999. If you scroll far enough, the calculator will eventually give up and tell you, bro, it's 1, because it's just going to round it to it. But it doesn't actually get there in this case, but it gets super close. So hopefully that helps you visualize these things, and I've showed you a variety of examples. I know it's kind of a long video, but I'd rather just do one big one there than chop it up into a lot of little scenarios. So showed a lot of stuff. You got any questions? Feel free to ask as always. Have a good day. Keep on living that limit life.